puberty meet based on interest. They pair you up with roommates based on your interest. So it's not terrible.
It's so nice.
What? You're an actual
Boss needs a real job.
Connor asked,
What?
what did you do?
He tried to pull the chair out from under me, but luckily, I didn't try. Luckily, I go like this to make sure that the chair's still there. I just looked, but
Probably was.
yeah,
Okay.
Dad raised me like this. Don't trust anybody. They're all out there.
Danny, are we still filming?
Yes.
All right. So with bulbs, we need to look at two different situations. So the first situation we're going to look at is you have a 100-watt bulb and you have a 60-watt bulb. And this is why I said when you deal with electricity, you have to focus on what is staying constant and what are you changing, okay? So if you start with the idea that power equals V squared over R, and by the way, you all need to be fluent in the three ways to calculate power. Pivot up, V squared over R, I squared R, okay? Because you just need to be able to work in these three interchangeably. Now, the only one that you actually have on your sheet is this one, but you need to be fluent in the three languages of power, okay? V squared over R, I squared R, and piv. So, if you keep the same voltage, so if you take this equation and you solve it for voltage, which is actually the square root of power times, I just realized that, that's power times resistance. So, if you look at it in terms of power times resistance, so if this is the situation, then if you're looking at a 100-watt bulb, okay, and the voltage is going to stay the same, like for example, in your typical household, you have 120 volts, okay, that's a fixed value, it's 120 volts. So then, if you look at this, then if you have the same voltage, and if you were to compare a 100-watt bulb to a 60-watt bulb, and the voltage is the same, which one's going to have more resistance? The 100-watt bulb or the 60-watt bulb?
This is for your package.
Okay,
I don't know.
just lay it on my chair, or put it over there, that's fine. Thank you. So, if the voltage is the same, as the power goes up, what has to happen to the resistance? It goes down. Okay, which seems, again, that seems a little bit counterintuitive. You would think, oh, more power, that would mean more resistance. Now, here's the other thing about bulbs, and we're going to do an entire bulb, or excuse me, we're going to do an entire lab on just bulbs. Okay, the brightness of a bulb is determined by power. So when you're comparing bulbs, the brighter the bulb, the more power that is. So if the voltage is the same, this is a huge if, then as power goes up, resistance has to go down. Now, the other side of that is that if you keep the same current flowing between the two bulbs, if you keep the same current, then, and if you look at power equaling I squared R, so if the power is the same, and let's just think this through. So if I've got a 60-watt bulb and I want to keep the same current. So if the current is the same and I got a 60-watt bulb versus a 100-watt bulb, and they're both going to have the same current, then what's going to happen to the resistance on the 60-watt bulb?
It's got to be less than the one on the 100-watt bulb.
Why?
Because you're going to multiply by a smaller number. And
Yeah.
get a smaller.
So if the current is, let's say, 15 amps, so if the current is the same at 15, the only way that I could have less power is if I had smaller resistance. Okay, so as you go through bulbs, that's one of the things that you have to keep in mind. Are you keeping the same voltage or are you keeping the same current? So generally speaking, you keep the voltage the same. All right, now we're going to go old school. Oh yeah, so old school.
Velocity, meters per second, please.
Oh, no,
No.
not quite that old school.
Gravity.
Atmospheres?
What? Oh.
Oh,
Wait.
no.
Whoa, thermo!
What?
Hey, I've been doing
Whoa.
pretty good. I thought we were doing good. I'm good on this.
Whoa.
Yeah, let's go.
Thermo. Because guess what? We're gonna need to melt some ice. What's that gonna require? Energy. Maybe from running a current through a wire that generates heat. Just saying.
A bare wire on the ice.
No, it's okay.
We're gonna do it properly.
Wait for the example I'm gonna do on Monday.
PK.
Oh, crap.
Oh, that's P ice. Row ice.
It's ice.
No, PK.
Ice.
PK. What is that?
It's the specific heat. We're not nuts. You knew yes I am. I'm 100% nuts. I look, you kind of had the
That legitimately gave me a friend.
What is this?
Okay.
What
So, you're gonna need this for one of the problems on your assignment. So there's two ways you can calculate thermal energy. One is mass delta T C sub P. So this is just gonna save you some hassle to look this thing up. So the specific heat of ice is 2090 kilojoules per kilogram degrees Celsius, okay? That's how much energy it takes to warm up ice. Anybody happen to remember the specific heat of liquid water?
4.184.
Yeah, pretty close. Around 4,100, 4,200 joules per kilogram. Now, anybody remember what LF stands for? Latent heat of fusion. So this is how much energy it takes to melt ice, okay? So notice that this number is much bigger, so it takes a lot more energy to melt ice than it does to change the temperature, because you got to dump a lot of energy into breaking bonds. So you're going to need these numbers for the assignment. Okay, speaking of the assignment. And yes, this is all it took me.
What's that?
Yeah.
What? That number is the latent.
Latent heat, that's the latent heat of fusion.
Of what?
And that's for everything? That's a constant?
No,
For water.
Just the water. For water.
It's the number you're going to need to do the
We
assignment.
need
That's
the
what I
CP
wanted.
for
I
water.
don't wanna dig through my non-existent
2000.
chemistry notes.
2009.
However damn long ago that was.
So I know what it sounds like.
I'm kind of disappointed that it doesn't talk about byproduct radiation at all though.
Is that 2019 or is that 2000?
Guys, don't worry.
Huh?
For the
3.33 times 10 to the fifth.
No,
That's 2090.
I thought this was, is this specific heat 2090 or 29?
That's for ice.
Yeah, because it of course has a different, that's how it works for some reason.
Probably just more.
Where's that at? I need that. How much energy?
Oh, and it's the kilogram number. Oh, that both feels right and physically hurts.
Huh?
Am I gonna hate thermodynamics on campus?
But it's a reason that they call it thermodynamics.
Call it what now?
I'm not having too much educating anymore, so I've taken one too many classes in one semester. I've been doing,
Okay, when you get to question 16, it's kind of an odd way that they have this diagram. So this is on question 16. So what it is they call it electromotive force, you can call it voltage. But you're asked to draw like how voltage changes as it goes through a battery, and you have like a series of batteries. So the basic idea is that each battery gives you a jump of energy, okay? So if you have like 3 batteries in a row, each battery would jump up the voltage. And then it's going to drop back down as it goes through a resistor. So this would be like you going through 3 different kitchens on the way to school. It's like, oh, I'm going to stop at home, then I'm going to stop at McDonald's, then I'm gonna stop at Casey's or Chick-fil-A, oh, that's nice, okay? And each place I'm gonna get some more food, and then when I get to school, I'm gonna consume it all when I go through school. So these are just 3 different kitchens. It'll make sense when you get to the problem. Okay, I'll give you a hint when you get to 44. On 44, when that's all said and done, because you have to find a time, that time should be around 400 seconds. That'll make sense when you get to it, but that's some serious complications. 44 is the most complex of the complications. So,
Complications where?
anyway, I'm done. You're on your own, be free.
Oh, there's